going to be if I take this cubic number and I do this canonical operation so it doesn't, which is going to give it back one turn, if I do it again? Doesn't it make sense that it would be a cubic number? I mean, can you imagine that it would be a fourth degree number? That sounds absurd. Or can you imagine even worse, that it would be a transcendental number? Made no sense to me. And so, but I wasn't able to make any headway, and so I'm going to offer a $200 prize to anybody who can prove that int of an algebraic number is algebraic to the same degree. Or, if you wish, the int of a transcendental number is transcendental. So that's something I don't know about. But one fact is for sure, that is that int has these jumps. Let me see. Maybe I should show one more graph. Yeah. If you this graph shows the where the copies are located by putting in vertical and horizontal lines so that there's a square wherever there's a copy. But it also has the property that it can define where int is for any rational number. That is, for half, it's there. For 2/3, it's that value. For 3/4, it's that value, and so forth. So you can define int using these lines to get it. Define it for all rational values as well as all irrational values. Now, the point that I wanted to make was simply that at all rationals, there's a jump discontinuity. But at all irrationals, it's continuous. Okay? And that was an interesting fact to me, very notable and very striking. And so, I think this is where this perhaps comes to an end. Oh, I guess it comes to an end because there's nothing left. So I can't go forward. So how do I get this off the screen?
Press escape.
Press escape? Oh. All right. And now how do I just hit the other one? And how do I go to get the whole?
View full screen.
Where is full screen?
Under the view menu.
What?
Under the view menu.
Under the view.
What is the scaling factor, or an asymptotic scaling factor?
Full screen mode.
Full screen is control A.
This? Okay, this is good. Let me go on. The scaling factor, I don't know what the question means.
I mean, you scale down by a certain amount, isn't it?
Well, yeah.
What is that number?
Well, basically, if you're between a half and a third, everything is just reduced by a factor. It's 1/6 as long. It's just, but the distortion. There's a systematic distortion. I'm not going to go into that because it would take too long. I mean, I was able to prove all these properties, the properties of int that said that it consisted of copies of itself that were twisted, and I did find the scaling, the thing that scaled that made it. It's a simple function. It's not that interesting. It was very exciting to me at the time, but I don't want to go into it now. What I want to say is that I want to tell the other part of my story, which is that after I did all these exciting things when I was at Stanford, I then went on to graduate school in mathematics at Berkeley, and I ran into a brick wall because it was far, far more abstract, and the kinds of things that I've been excited about were completely of no interest to anybody at Berkeley. There was a total snobbery, and it was clear. I mean, and I respected the math that they were doing, but it was above my head. It was too hard, too abstract, and so I wound up dropping out of graduate school in mathematics, and after some great deal of soul searching, I wound up changing into physics, making a kind of a dare, because physics is still mathematics in some sense, and I was going into theoretical physics, and I was still hoping that even though I was still going to be in a kind of mathematical area, the mathematics would be more concrete, less abstract than what I've been exposed to in my, the courses that were required of all graduate students at Berkeley. And for the first couple of years, I was very excited. And I entered physics with a very strong prejudice, which was that the only kind of physics that is of any interest is particle physics. that all the rest is engineering. And I was very, very convinced of this. I was very, and so for years, I tried to become a particle theorist, but it got more and more repulsive to me, and I don't want to go into all the details. I found it more and more to my distaste, and finally I remember the day on which I bowed out. It was a very bitter day, but I really said I quit, literally. And but I didn't know what I was going to do. At that point, I invested 6 years of my life in graduate school in physics, and I had no idea what I was going to do if I didn't continue. And one of my friends who had gotten his degree at Oregon, that's where I was, I also moved from Berkeley to Oregon. One of my friends who had gotten his degree at Oregon with Gregory Wannier suggested that Wannier was a very interesting and lively person, and I knew Wannier a little bit, and I agreed that he was an interesting and lively person. He was in solid state, though. This was sort of the slumming it to the maximal degree. I mean, what could be more engineering than studying the properties of solids? It seems so unpure. But my friend was able to get partway to convince me by saying, look, it's the study of how macroscopic properties emerge from microscopic properties. Emergence is a beautiful phenomenon, and there are great mysteries in how does the macroscopic world emerge from the microscopic. And that was the first step in convincing me that it might be possible to explore solid-state theory after all. But what really did it for me was somebody else who I don't know who it was, but it was a graduate student at Stanford who I was talking to about this. And he said, crystals are very interesting. They're like discrete vacua. Like particle physics happens in a continuous vacuum. There's just empty space. But solid-state physics has different vacua, different vacuums, if you wish. They're just crystal lattices. They're discrete vacuums instead of being continuous. And so all of a sudden I thought, oh my gosh, it's similar to number theory. It's like I love the integers because precisely they pick out a discrete lattice along the real line, and a solid picks out a discrete lattice in space. And he said all the same things happen in solid-state theory as in particle physics, but on a discrete lattice. And all of a sudden I was pushed over the brink. I thought, oh my God, okay, I'm going to be doing number theory. In a certain sense. Now, I went to Gregory Wannier and I asked him about what I might do. He had several problems. And one of them was this problem that had to do with a crystal lattice in a magnetic field. And he said there was something about rational and irrational fields that was very different. And my ear perked up at this, of course, because I was very interested in rationals and irrationals. But also I knew that it made no sense for there to be any difference in physics between irrational and rational fields. Certainly nature can't tell the difference between an irrational and irrational field. I mean, you don't go around asking people, do you prefer being in irrational temperatures or rational? It doesn't make any sense. But I was intrigued. I was very much drawn to this idea, and so I decided to risk it and to go into this, exploring this thing. So here is a picture of the magnetic field going through a square. Let's assume it's a square lattice, and there's a certain amount of flux, which you may know about if you took your physics courses. It's the area of the square of the lattice times the value of the magnetic field. So that's the amount of flux that's passing through a unit square of the lattice. Now, it happens that quantum mechanically there is a natural unit of flux, which is defined by the product of Planck's constant, the speed of light, divided by the charge of the electron, and that has the units of flux. And it's a natural flux thing. So you can measure the flux that has some units attached to it in terms of this thing and get rid of the units. It gives you a pure number. And this can also be thought of as a ratio of two natural temporal periods associated with the this situation. That is, if an electron is in a magnetic field, it has a natural thing called a Landau frequency. It wants to go in circles, so it has a natural period. It is the time it takes to go around in these circles. Or if an electron is in a crystal, it has a natural period associated with the crystal that has to do with, it's too complicated to go into, but there's a natural period also associated with the crystal. And you can take the ratio of those two natural periods, it's the same number. So in some sense, it's like there's a conflict between two periodicities. One would be due to the magnetic field alone, and the other would be due to the crystal alone. And it's a fight between these two periodicities that doesn't. Now, I don't have any time to tell you how to derive the equation that governs such a system, but this work had all been done before, and basically what I've shown here is that this is the Schrödinger equation in a sort of a disguise. The first two terms are in effect a second difference operator, which corresponds to a second derivative, second spatial derivative. This is because it turns into a one-dimensional problem. The way that happens is that you can just whatever the term is when you write down the wave function as the product of an x part and a y part. And the y part turns out to be trivial, and so you can get just one dimension is of interest. And this is the periodic potential. This is the Schrödinger equation. That sort of represents the del squared. This represents the This represents the potential energy function, and the epsilon is the eigenvalue for the energy. And so the alpha, which is the magnetic field measured in this dimensionless fashion, is up there. K is the spatial variable. K is just a number that's moving along in space. It's just what lattice point are we at. So K is the equivalent of X as a spatial variable. So that's what K is. So 2 pi is a constant. K is the spatial variable. Alpha is the magnetic field. And the nu is a little random extra thing that's not important for our purposes right now. I should have left it out. And epsilon would be the eigenvalue. That's the Schrödinger equation in a kind of in this situation. So you can rewrite it in this fashion. I put psi of k plus 1. For some reason, I replaced psi by g. I don't know why I changed it from psi to g. Anyway, it doesn't matter. So you can rewrite it in this fashion, and that can be, the top line is just the same line as I had before. I left out the nu, I see, for me. The next thing is just a restatement of it in terms of little vectors of size 2. The m plus 1 and mth value can be gotten from the mth and the m minus first one by multiplying by this 2 by 2 matrix, which we can call A sub m, which has epsilon as a sort of as a parameter. I mean, alpha is also a parameter, but alpha we're considering to be constant right now. So alpha is a constant, so epsilon is a variable. We're looking, what we want to do is find the epsilons for which this, the eigenvalues at work, and I'll explain what I mean by that. Epsilons are the eigenvalues we're looking for. So this is a 2 by 2 matrix, gives you that one, that little vector from that little vector. So if you can move backwards by getting this, by doing it recursively. You can replace this by a matrix by the previous one, and then another matrix by the previous one. So you can get a product like that, where it goes m matrices to get that thing. Now, if alpha is a rational number, then these matrices repeat after, if it's P over Q, then these matrices repeat after Q steps. They just do the same thing over and over again. So you have sort of a fundamental matrix, which is the product of these Q matrices, which is saying if you want to go Q steps, just multiply by this long thing, which is Q matrices long, and you just do it over and over again. You just put that matrix to a power. Well, it turns out that then the question as to whether the wave function will remain bounded is a question of whether that matrix put to a high power will have a finite trace, or a trace which is bounded. And so that's what it all turned into. It all turned into a question of for which epsilon values is it such, when you have a rational field, for which epsilon values is it the case that you will get the trace to be less than 4. That was the condition that had been found by other people, not by me. And so when I was working with my Ph.D. advisor and some of his colleagues on these questions, I was trying to do what they were doing, which was to manipulate this equation and prove theorems about it. But I was way out of my league, once again, totally out of my league. But I happened to stumble across a little computer in the hallway. It was just sitting there unused. And I decided, well, one thing I know how to do is look at numbers. And so I decided to look at some numbers instead. And so this is a case where alpha is 1/3. The magnetic field is effectively 1/3, and it gives you a polynomial. The condition on the trace is a polynomial of degree 3. And what you're asking is that the polynomial should be in absolute value less than or equal to 4. So what effectively that means is that you fatten the x-axis up to be, instead of a line, it's now a fat axis. And you're asking, when does this polynomial pass through the fat axis? For what x values? And you get fat roots. So here's a fat root, here's a fat root, and here's a fat root. You get 3 fat roots. And my old friend John Mather came to my help at this point, and he proved a technical theorem here about these things, which I won't go into, but which is that the roots never overlap. They can at best kiss and touch each other, but they will never overlap. The fat roots will never overlap. They will always be separated from each other, or at the most will kiss. Anyway, that's neither here nor there. This is 1/3. This is 1/5. Now, what's interesting is that since you get for P over Q, you'll get 5 fat roots, which are bands, as they go. Energy bands is what it comes down to. 5 energy bands if Q is 5. But 1/5 gives this, but 2/5 gives this. This is what you get for 2/5. So you have 2 on the left and 1 in the middle, and then 2 on the right. In general, for 1 over n, or 1 over q, let's say, they will be roughly equally distributed. Not exactly, but roughly equally distributed. Whereas for other fractions, p over q in general, as opposed to 1 over q, they will be grouped. So here, well, this is the beginning of the spectrum that I saw, just showing you things that I've already mentioned. So if there's no magnetic field, you get a very big band. If there is 1/5, you get 5 bands. If they're 1/4, they get 4. They 2 kiss in the case of 1/4. If it's 1/3, you get 3. 2/5, you get something like that. So that was what I started doing. I started just drawing graphs like this, given numbers on the computer. Still no plotter. Well, this I don't want to explain. Okay, this is 3/19. Now look at the y-axis. You can see this is a crazy polynomial. It's supposed to have 19 across the axis 19 times, which it does. But it looks like it crosses it only about 3 times. But that's because this is such a gigantic scale. This is a million. But if you look at the inner part of it, this is now where it's on the scale of 2,000, and you can see more structure. And this is now where it's on 50 and minus 50. Now you can see that it's crossing the axis a bunch of times. Here it's doing it so quickly that the 3 times you can't tell. But here you can see the 3 times, here you can see the 3 times, once, 3, 3, and 3. So you get 19 crossings, 19 fat roots. On the left side, it's basically imitating 1/3. It's basically imitating 1/3. It's imitating 1/3. Then 1, then 1/3, then 1/3, 1, 1/3. So you basically have sort of a fractal kind of a polynomial. And I'm not going to skip this. And this is the full graph of the spectrum with the, I showed you before, I don't have the line here. There should be a line here at the bottom, which represents 0 magnetic field. Anyway, at magnetic field 1/3, you have 3 bands. At 1/4, you have 4, which kiss in the middle. At 1/5, you have this, and so forth. And this was the structure that I found, and I I didn't find this immediately. I graphed this at approximately 1/100th of this grain size. In other words, I had far, far, far fewer lines. And I could see the structure because I was familiar with int. And I recognized it instantaneously. And I showed it to my advisor, Gregory Wannier, and he said, "You're talking nonsense. This is numerology." He said, "You won't be able to get a Ph.D. thesis. You'll have to write a library thesis." And I said, "What's that?" And he said, "Where you write up other people's things, and if you want, you could put your numerology in an appendix." Well, I then decided, he didn't know what he was talking about. Over the next few months, what I did was I was able to calculate a lot more and to use a real plotter. This is, of course, done with a real plotter, and I was able to take this kind of an area, just as with int. I was sort of able to take this whatever they call it. It's not a rhombus, what do they call it? Trapezoid, and to sort of expand it into a rectangle and to show this is what you get if you rectangularize the contents of that trapezoid. And if you go back down into one that's down here, between a 6th and a 7th, I think it's down here. So that's what the thing looks like. That's the area around it. Inside, if you rectangularize it, you get that. Of course, the fewer lines. But you can see the structure coming back. It's a distorted structure. So by showing this to my advisor, finally at some point the scale fell from his eyes, and he understood that indeed we were dealing with a fractal structure which he had never heard of. The term didn't exist at the time, and so then if you smear the graph, if you jiggle it, you might say, just a little bit, all of the fractal structure goes away, and you're left with just something that looks like that. If you jiggle it a little less, you get that. If you jiggle it less, you get more and more fine structure. And if you jiggle it not at all, you get the original full fractal graph. So this was the resolution of the problem that nature doesn't know what the magnetic field is to infinitely many decimals. So nature sees something like this.
So that was before the Michael set?
What's that?
Yes. That was before?
Yeah. Well, I don't know when he discovered it. It was before any of his books were published. I don't know when he discovered it. Yeah, I think he discovered Mandelbrot in 1980. So this is about 5 or 6 years before that. Yeah.
So you anticipated Harper?
Well, so did Peano, so did lots of people. Snowflake curves, anyway, I guess that's enough. I just wanted to give you this story. I probably have overshot, but maybe not. Maybe roughly. So thank you very much.
Questions for the speaker?
Yeah.
So, for any sequence of, I guess, what were they called? Counted set.
Yeah.
Can you find
For any sequence of positive integers greater than 1, I mean, they have to be 1 and 2 at the minimum. But if you write down any arbitrary sequence of integers for count, and then any arbitrary sequence that's 1 away from it, has to be either one above or 1 below. But as long as they're all at least 1 in size, they always define a real number.
Regarding your conjecture about that if it's an algebraic number, you conjecture, what's the question that it's algebraic? Well, what's your feeling?
No, my conjecture is that if it's algebraic of degree n, then int of it is algebraic of degree n. It's just that my conjecture was not supported by my computer experimentation, because I took cube root of 2 and I calculated the int of it, and then I plugged it into a whole bunch of the equations. I mean, all the equations that have fairly small coefficients, and it didn't give 0 for any of them.
So do you have any evidence why it should be?
Just my intuition.
Computation methods for counterexample?
Oh, yeah. Absolutely. For sure. But it's hard for me to believe, that, but then what do I know?
Any other questions? Well, let's thank the speaker again.